I don't hear anything. Is that right?
Okay,
Hello?
muted. But now I'm unmuted and you can hear me, I assume. Yeah?
Yes, good to go.
And okay, so feel free to ask questions in the chat. I'll try to pull it up so I can see it. And if they seem topical or relevant to what I'm trying to say at the moment, I'll try to answer it at the time. So if it's a clarifying question like, hey, what's a bit? What's a qubit? It'll probably be something I'm going to try to talk about in my talk. Otherwise, we'll have open questions at the end. And if for some reason you can't hear me or the audio cuts out, please wave your arms and unmute yourself and let me know. This seminar series is co-sponsored by the Center for Quantum Sensors. This is a center a few colleagues of mine and I founded in the physics department just the last few years. And the center is focused on recognizing the incredible power in the scale and complexity of quantum systems and trying to use this complexity and this power for scientific and technological advances in all areas. And that's really what I want to convey to you in this talk today is how incredibly exciting the potential is for quantum technologies in the coming century. Quantum theory, that is the theory of physics that describes the microscopic world, is now well over 100 years old. And many would argue that it's the best theory that we have to describe our physical world. And what's exciting is that this century, we've just started to develop the experimental capabilities to control and harness this sort of quantum physics world. And this is the beginning of what we call the second quantum revolution. That is, the 20th century, we might regard as the first quantum revolution. Silicon transistor technology, which enables these fancy devices that I use to give my presentation, connects us across the world for this lecture, is, at a fundamental level depends on how electrons are transported and semiconductors, requires an understanding of quantum physics. But quantum physics sort of plays a back seat in silicon transistor technology. That is, it's not, the weirdness of quantum mechanics is not at the forefront, it just sort of underlines the basic physics. Our hope is that the 21st century is going to be the second quantum revolution, where we harness the sort of quantum weirdness and the strange properties of quantum mechanics in true quantum enabled devices. And as I'll say in this talk, quantum mechanics has an inherent complexity that's much beyond what we observe. That is, if you take just a modest array of quantum particles, you can end up with a situation where to accurately describe what's going on requires more parameters than there are particles in the observable universe. And of the second quantum revolution is to harness this incredible complexity, harness something that you can't ever possibly understand exactly, and use that to really do fundamentally undoable things. To give you a sense of what's so exciting about the second quantum revolution, I want to go back to a story about the origin of chess. Now, as I heard the story, there was a scholar who invented this amazing game, chess. So much more interesting than backgammon or whatever they played at the time. And the king was so delighted with this new game, he asked the scholar, what would you like as a reward for your incredible invention? And the scholar thought about it and said, why don't you give me 1 grain of rice for the first square, and then 2 for the second, and 4 for the third, 8, 16, so on and so forth. You get the point. The king says, sure, no problem, we can do that. Until he goes and talks to his farmers and his treasurers, and they realize that that much rice is over 2,000 times the current annual production. So well more than all the rice that's been produced since that story was first told. an unfathomably large amount of rice. And what that gets at is the fact that 2 to the n can be quite large, because what we have here is 2 to the 0 is 1, 2 to the 2 is 4, over here 2 to the 4 is 2 to the 2 is 4, 2 to the 3 is 8, and so forth and so on. We go all the way up to 2 to the 64, and that becomes a very large number. And that really highlights the power of exponential scaling, that we don't live in a world of exponential growth. We have no intuition for it in some sense. And so the fact that 2 to the 64 is an unfathomably large number, it just doesn't stick in our heads. And that's the power we want to harness in quantum technologies. A little less than a year ago, quantum mechanics made front page news in the New York Times. It's this article down here where Google claims a computing feat akin to first flight. Turns out that first flight was actually second page news. So obviously it's even more important than first flight. And I'm going to use the story of what Google did as a way to unpack what's so exciting about quantum technologies. But before I can explain what Google did and why it's so interesting, we have to back up a little bit and just talk about how normal computers work. So as I'm giving this presentation, I'm using my Macintosh computer, and I did a little research, and it's apparently a 64-bit operating system. So what does this mean? Well, it means that the registers and the address buses and the data buses are all 64 bits. I don't know much about how a computer works, but I do know what a bit is. A bit is a 0 or a 1. And so what it operates on is it has these sort of strings of bits, 1, 1, 0, 0. Okay, and so things go in, it does some calculation, and it outputs a 64-bit word, perhaps, what you call it. So, for example, if I ask, hey Siri, what's 5 plus 4? Well, Siri doesn't just do 5 plus 4, go deep into the computer. This problem gets converted into binary, where 5 is written as 0, 1, 0, 1, and 4 is written as 0, 1, 0, 0. And then the computer does addition in binary. So it's actually very similar to adding normal numbers. You know, 1 plus 0 is equal to, or what is it equal to? Is equal to 1, right? And 0 plus 0 is equal to 0. Now 1 plus 1, will that be equal to 2, but we're stuck in binary. So we put a 0, we carry a 1, we end up with 1, 0, 0, 1, which turns out to be binary for 9. The point of this is to show that it's a very simple operation to build addition into binary. That is, you just, you see what, you take the larger of these two. If the two are the same and they're both 1, then you carry the 1. So you can think about how you build logic circuits that would add numbers. Okay, back to Google. Google built a 53 qubit chip. It's a gorgeously beautiful device. It has an engineering feat that really boggles my mind, and I'm a researcher exactly in this area of technology. It's got lots of wires. You can't see what's going on because the inner chips have wiring come from the top and the bottom, so it ends up looking kind of like a normal computer processor almost. But what's special about 53? Well, it's less than 64, but these are qubits. So here's what you need to know about qubits. It's a compound word. Okay, the bit part, we talked about this. This is going to be 2 states, and they end up being, in their experiment, 2 energy levels of some sort of superconducting circuit. We won't get bogged down in the details. And then there's the Q part, which stands for quantum. And that means that those 2 energy states can exist in a quantum superposition. Okay, so whereas a normal bit, as we have in our computers, is always just a 0 or a 1. But a qubit can be in a superposition of these 2 states. And to remind ourselves that we're talking about qubits and quantum states, we put this funny little structure around them. We call it a ket, it's a line with a little bracket. And so you can have a qubit exist in some sort of superposition or just a linear combination of these 2 states. So some complex number A times 0 plus some complex number B times 1. Okay, it's kind of hard to get a sense of what this is or why this is interesting until you get to start to see examples of what these quantum superpositions are like. And I can do that pretty well by way of an analogy. That is, here's a drawing of a cube. Now, looking at this cube, you can interpret it in two ways. It could be facing down to the left, or it could be a cube facing up to the right. What's so interesting is that before we make a decision which one we want to see or which one it looks like, it really both possibilities exist at the same time. It's ambiguous. But once you stare at it, okay, look, oh, it's a cube down to the left. Oh, it's a cube up to the right. And that's also an aspect of quantum superpositions that we see when we measure them. That is, we may create some combination of 0 and 1, but when we measure it, we'll get a classical bit out, a result, 0 or 1. And we get those with a certain probability. It turns out the probability of getting 0 is this related to this coefficient squared. The probability of getting 1 is related to this coefficient squared. Okay, so this is just the peculiar rules of quantum mechanics. And we'll use those to understand why Google's result is so interesting. Okay, so back to Google. They built a 53 qubit chip. They call it their Sycamore processor. One way to think of it is you see all these wires coming in here, right? And they initialize all 53 qubits in some initial state. Maybe they're all in the state 1, 1, 1, or they're 1, 0, 1, 0. They're initialized in definite energy states. And then all sorts of stuff goes on. We're going to get into the details of that to some extent. And then they measure what are the outputs of these. And when they measure them, each qubit gives a classical bit answer. So one of them says 0, next one says 1, so forth and so on. They get 53 zeros and 1s. So when they press go on their circuit, 10 microseconds later, it spits out 0, 0, 0, 1, 1, 0, so forth and so on. Okay, these are the results of qubit 1, qubit 2, qubit 3, qubit 4, qubit 5. Okay, they do it again. Oh, now they get 1, 1, 0, 1, 0, 1, so forth. It's a different string of bits. Doesn't seem like it's a very reliable machine. They do it again. Now they get a different pattern of zeros and ones. And they do it again, get a different pattern of zeros and ones. And they do it again, a different pattern of zeros and ones until they do this enough times and they start to see that some patterns of zeros and ones appear more often than others. So it's not randomly giving zeros and ones, but there's some structure to it. And if they run this millions of times, hundreds of millions of times, it only takes a couple hours to do. They can determine the probability that we get this string of outputs compared to the probability of this string of outputs. So it's a machine that experimentally samples probabilities. It says the probability of this 0, 0, 1, 1, so forth, so on is X. Now, what's so intriguing is to calculate these probabilities from, say, first principles, or any way, is incredibly challenging, impossibly challenging. And this has to do with something called entanglement. So let me explain how this works in the context of Google's experiment. So they've got this input here where they have 53 qubits, right? And sort of the circuit that we're going to draw, it has time running on this axis. And let's just look at the first 2 qubits at first. What they do is they apply something called a quantum gate. What that means is they let this first qubit interact with the second qubit. And now the two, since they've interacted, become one quantum state together. So we can't necessarily think of them separately anymore. And so now, if I think about the joint quantum state of both qubits, there's 4 basic options. We could have the first qubit is 0, the second qubit is 0, or we could have 0, 1, 1, 0, and 1, 1. Those are the 4 possible combinations of these qubits. And because it's now one quantum entity itself, stuck inside this ket symbol, it means we can have a superposition of all 4 possibilities. So we can have 0, 0, 0, 1, C times 1, 0, all sorts of different coefficients. And now they run the circuit and they measure what is the state of the first qubit. Well, the probability that it's a 0, we just look at the state where first qubit's 0, another state where the second qubit's 0, first qubit is 0. And so we get this coefficient A plus the coefficient B, and then we take the square of the 2. Thanks, Phil, for the answer to the question. Okay, so that's what happens with 2 qubits. What does it look like with 3 qubits? Well, now we let all 3 qubits interact. So they form one 3 qubit state. And now there's 8 possibilities, 0, 0, 0, 0, 0, 1, 0, 1, 0, and so forth and so on. And so this system now could be, in general, in any linear combination of all 8 of these states. I got tired of writing them. And now the probability that the first qubit is in the 0 state, well, I look at amplitude A plus amplitude B plus amplitude C, but not amplitude D because this is an excited state, 1 state. But this one here, which I would label E, is, so it's A plus B plus C plus E absolute squared. Okay, so now we'll look at the whole circuit, all 53 qubits become entangled with one another. Now, the probability that the first qubit is in the ground state, is in the 0 state, well, it's A plus B plus C plus D plus E plus F, so forth and so on, all the ones where there's the ones in 0 state, and we have all these other combinations. It turns out that there's 2 to the 52 different coefficients we have to include. So I run out of alphabet really quickly. 2 to the 52, how big is that number? Well, it turns out it's 4 quadrillion. It's a big number. You need 4 quadrillion different complex numbers to figure out what is the probability that the first qubit is in the 0 state. If you want to know what the probability of the first qubit in the 0, second qubit in the 0, and a third qubit in the 0, so on, well, then I need all 8 quadrillion different complex numbers. Each one of these things depends on a different combination of those. Sorry about that. Try to turn off notifications, it doesn't work. Okay, so 8 quadrillion different coefficients. And Google estimated that it would take 10,000 years to calculate those coefficients on the fastest computer that you can get on Earth. 10,000 years to do something that their machine does in a matter of hundreds of seconds. IBM, which turns out to be a competing group in the same technology, says, well, we just built this new Oak Ridge Summit computer and you use it in a specific way and you could do it in a couple of days, maybe a week, maybe a month. So they were a little annoyed, but still, Google's computer does something in 100 seconds that takes IBM, maybe, best case, several days to do. And the way they would do it is their computer has so much memory, they can write down all of the coefficients and just sort of brute force calculate it, what's going on. This question about the imaginary component of the coefficients, and it's a good point that these coefficients, A and B and C and D, those are all complex numbers. And there's not any particular significance to the imaginary versus the real. It's just a choice of phase. So we can think about them as purely real. It's not going to make a big difference in our outcomes. Okay. Google, I have to now reshare my screen. Had 53 qubits. They'd only have to make this system roughly 5 times as big, and they could get to 266 qubits. Now, 266 qubits is a big number, which is why I made it so big. Why is it big? Because 2 to the 66 is about 10 to the 80. So 10 with 80 zeros on the end of it. And 10 to the 80 is widely accepted to be the number of protons, neutrons, electrons, neutrinos, all the particles in the observable universe. An unfathomably large number. And a processor with 266 qubits would then require that many parameters to predict with what's going to happen. This is this incredibly absurd complexity of quantum systems. Can we use this for anything? Okay, so it's complex, it's controllable, but is it useful? Well, one use case has guided quantum technology for the last several decades. And that's something called Shor's algorithm, which is about factoring numbers. So here's the story. Every night, I give my son a math problem. And if I'm feeling kind of mean, I'll give him a problem like this. Hey, West, what two prime numbers do you multiply together to get 491,597? And he sighs, like, well, okay, is it divisible by 2? No, that's easy. Divisible by 3? Well, let's do a long division problem. Is it divisible by 4? And so forth and so on. And it takes a lot of different numbers to check until he figures out what two numbers you have to multiply together to get that number there, because each one involves its own division problem. On the contrast, if I'm feeling nice, I'll give him a multiplication problem like, what's 593 times 829? Okay, multiplication problem takes him a few minutes, and you might find, oh, look, it's the same answer. That's the answer. It's 491,597. So the point is that factoring large numbers, or the products of large prime numbers, is really hard because you kind of have to guess and check. But it's easy if you have the factors to check that that's the right answer. In fact, it's a professor's perfect problem. And this sort of hard one way, easy the other way, is a really useful tool in encryption. And in fact, this is the basis of 2048 RSA encryption, which is how our bank accounts and all sorts of things are encrypted these days. It involves prime numbers that are 2048 bits long, so very big prime numbers, possible to factor in any amount of time on the most powerful computers. And so they make good encryption. And so Peter Shor in 1994 pointed out that, but look, if you're really clever, it turns out that these quantum computers can factor these large numbers into primes exponentially faster than the way normal computers do it. Okay, or another way to say that is it becomes exponentially harder for a normal computer to factor larger and larger numbers. But Shor's algorithm shows that a quantum computer could do this in what they call polynomial time. This just gets a little bit harder each time you make the number bigger. And so what would take a normal computer a millennia to factor, a quantum computer could do in a matter of hours. That's kind of cool, but it has to do with just breaking codes and encryption. But it's a demonstration of real exponential advantage or principle. Turns out that this is still a technology that's far from being useful. Because if we want to factor a 2048-bit number, it would require a quantum processor using millions of qubits. Okay, and Google has a quantum computer with 53 qubits, and the quantum computer they have doesn't quite work well enough even to factor numbers that are much, much smaller. Okay, so this is still a very distant possibility of factoring large numbers with a quantum computer. Is there anything that's more useful in the near term? That is, we have this incredible complexity with the potential for exponential advantage, just from the fact that the Hilbert space, or the number of states or coefficients we need to keep track of, scales exponentially with the number of qubits, 2 to the n. Can we use this in any way for something practical? And I'm going to give you 2 examples. First example is, actually both examples have to do somewhat with looking at black holes. The first one is how the Laser Interferometer Gravitational Wave Observatory, LIGO, is now using squeezed light, which is actually the same quantum entanglement that underlies the complexity in Google's processor. And the second is an even crazier idea that maybe we'll use in the near future to build telescopes that can see things you couldn't imagine seeing any other way. So, LIGO. So LIGO is this gravitational wave interferometer. And last year we had a really wonderful public lecture from Kip Thorne, who won the Nobel Prize for his really conception and driving of this project for so many years. And he said that, you know, quantum squeezing is now a key technical tool for the LIGO interferometer. So let me give you just a sense of what that is and why that's important. Now, the LIGO interferometer is an interferometer. What does that mean? Well, we shine a laser beam on a beam splitter, and it bounces out two arms of these mirrors and interferes. That is, the laser is some sort of wave. Some of it goes through, and so we have some smaller amount here, some going up here. They reflect off the mirrors, so the light's coming back, and the two light beams from the two arms are aligned such that they interfere perfectly destructively. That is, the peaks and the troughs counteract one another. And so there's really no light coming to this photodetector here. Now, if a gravitational wave comes through, what it does is it stretches this interferometer. So one of the mirrors gets displaced by the smallest amount you could possibly imagine. And that changes the phase of the reflected beam, which breaks the perfect destructive interference observed in the photodetector. And from that, we can infer what the positions of these mirrors are versus time. And that gives them their signal, which allows them to detect gravitational waves. Now, it turns out that quantum mechanics is very important to this very large interferometer. And the first piece of it is that light is actually quantized into photons. That's why we call it quantum optics. So light has both a particle and a wave nature. And the thing about photons is they don't interact with one another. And so if we think about a laser beam with a certain amount of power, since each photon carries a certain amount of energy, we can turn that laser beam with a certain power into like a number of photons per unit time, 1,000 photons per nanosecond, 100,000 photons per nanosecond. But the photons, they don't interact with one another. So if I break that time bin into even smaller chunks, first chunk, second chunk, third chunk, the photons get somewhat distributed randomly in there. And so it's like flipping a coin. Does the photon go in bin 1, 2, 3, or 4? And when you randomly distribute the photons, they end up not evenly aligned, like 2, 2, 2, 2, but instead with the fluctuations in how many photons are per unit time, because they can't coordinate with one another. So really, when we think about this interferometer, we have to picture lots of individual photons moving through the interferometer. So we send in a laser beam. Some of the photons go this way, some of the photons go that way. And the photons have two kind of important effects. The first is that these photons carry momentum. And so when it reflects off this mirror, it gives a little kick to the mirror. And this one reflects off this mirror, it gives a little kick to that mirror. And so the photons start pushing the mirrors just the same way that the gravitational waves do. So the mirrors are wiggling around due to the light. That's called radiation pressure noise. Also, the fact that the photons have random arrival times, for example, leads to some sort of randomness in the noise here. So the photodetector, which is looking for changes in the intensity, really the phase or quadrature amplitudes of the light, has some fundamental noise to it, which we call shot noise, which is due to the fact that the individual photons are, that the light is quantized into photons. And it turns out that it's actually due to vacuum noise entering in through this port here. So it's some vacuum fluctuations, details we don't need to really know about. But what I want to tell you is that LIGO has figured out a way to send entangled photons into the system from this vacuum port. And the entangled photons means they have certain relationships between one another. This photon with this certain complex coefficient, this photon with this certain coefficient, and those entangled photons are set up in just a way to cancel out the noise from the fluctuations in the photons in these interferometer arms. So they use the entangled structure of the photons to reduce the noise in their detector. And they've been doing this for some amount of time. Here's a graph from 2013. And what I want to show you is that here's the noise floor of their system without squeezing. Now they add in entangled photons, and the noise floor gets decreased by a little bit. Okay, but a little bit actually turns out to be somewhat consequential, because that means they can look a little bit further in all three directions of space. And so they get a little bit further cubed. So if they reduce their noise by a factor of 2, that means they actually get to see 8 times as many gravitational wave events. Okay, and so this is actually now a key technical tool that they're always using the squeezing. Why would they not? But they're harnessing this complexity in the correlated nature of photons in order to cancel noise. Okay, and so yeah, what does LIGO do? They look at black hole mergers. They look at other types of mergers, but largely they're seeing all these black holes, and it's really exciting, changing the way we do astronomy. So that's one way to look at black holes. Another way to look at black holes is to look at them directly. And so just a few years ago, we had another really amazing detection or observation in astronomy, which was the observation of the event horizon of a black hole, a very large black hole in a somewhat nearby galaxy. And this is a picture of the event horizon of that black hole. It has this beautiful sort of shape, kind of indicating that there's something going on here. And we're lucky enough to have Michael Novak as a member of our physics department, who is a part of the team that worked to make this amazing observation. And so I called him up on Zoom on Thursday and asked him, just tell me about what you did. This is so cool. He says, well, the thing that's so amazing, Kater, is this is a telescope with 20 micro arc seconds of resolution. Okay, so that's some sort of angular resolution. You want to know how big 20 arc seconds is? Take a black hole 100 million years to 10 million light years away, and that's, think about how big that is in the sky. That's 20 micro arc seconds. It's really small angular difference. He says we're able to see this because of this incredible resolution. And you won't believe it, but in order to have resolution that high, you need a telescope the size of the Earth. Okay, so you normally see these telescopes in these arrays here, and I'll get into why they build an array of telescopes. But they actually made an array of telescopes that was as big as Earth. There were 8 telescopes when they made this discovery, or this observation. Those telescopes working in coordination were able to see this black hole event horizon. Now it turns out each telescope recorded so much data, they had to actually put the data into hard drives and fly it in an airplane from all the different places to be worked on in one place, because there was more data than they could possibly send over the internet. Pretty cool. Okay, why do they need a telescope the size of Earth? Well, this is something called the Rally Criterion. Okay, don't be afraid. It's a very simple equation. It says that angular resolution is related to the wavelength of light that you're using. And then D is the size of your aperture. And so in this case, they needed a D that was as big as the Earth. Okay, so the way to think about that is if you think about a camera or a normal telescope, your resolution is set by the size of that aperture. So that's a size D. And what's going on is because light has wave nature, it has some third thing here, and the light interferes along 2 different paths. And so if I shift the location here by some angle, that'll change the path. And the bigger the aperture is, the more resolution, the smaller the angle we have to change to get constructive or destructive interference. Okay, so it has to do with the light interfering with the different paths and the different apertures. Okay, so the Event Horizon Telescope uses something called a synthetic aperture. That is, they have a detector here, and it records the wave that comes to this detector, and this one records the wave that comes to this detector, and then you can, later on, put all this data in a suitcase, and you say, would the 2 have interfered constructively or destructively? Okay, so they just record here and they record here, and they record exactly the amplitude of the light that comes in. Now, it turns out that that's possible to do at microwave frequencies, where things are relatively slow compared to the clock rate of computers. You can say, okay, it's going like this, it's at this phase, but it's actually impossible to do at optical wavelengths, just because the frequency is just way too high. And so if we want to do a synthetic aperture with optical at optical frequencies, with optical telescopes, you actually have to connect these two with some sort of thing that brings the light from one detector to the other detector. Okay, so that we can see if it interferes. And this is actually the approach taken in the very creatively named Very Large Telescope. They've got an array of telescopes, and the light actually is piped between the different telescopes, and they see, does it interfere or constructively or destructively. In fact, this telescope played a key role in this year's Nobel Prize in physics, which also has to do with the observation of black holes. Okay, so here they're able to put these telescopes, of order, say, 10, 50 meters apart. And it's limited by the fact that they need to, probably in vacuum, it's very challenging to bring the light together to interfere. The point is that it's the light, no matter what you do, is sort of exponentially attenuated as you move it further and further and further. Okay, so you could say it becomes exponentially harder to move the telescopes further apart. 10 meters, 50 meters possible, but the size of the Earth, not possible. And the reason I mentioned this problem in an exponential way is because it sounds just like the problem with factoring numbers in some sense. It's exponentially more challenging to factor larger and larger numbers with a normal computer. Is there a way for quantum technologies to help overcome this exponential hurdle? And there is, which is why I'm telling you about it. The idea is to now connect these two telescopes, not with a fiber that moves the light from one telescope to the other, but with a pair of entangled photons that establish a connection between the two telescopes, that entangle the two telescopes, so that we can tell the light that comes in this telescope, would it interfere with the light coming in this telescope without ever having to move the photons between the two. It's the same sort of entangled state we saw before, where we have a 0, 1 plus 1, 0. We create those entangled states with photons in these two telescopes, allowing them to have a synthetic aperture that's now not limited by the challenge of moving photons between one place and the other. And this is the idea behind quantum-assisted telescope arrays. I heard an amazing talk on this by a brilliant graduate student, Emil Habulabin, who's at MIT. And he points out that with some really clever tricks using things called quantum memories and simple processors involving just a few qubits, the technology to do this sort of thing, to entangle telescopes with long distances between them, is nearly available today. That is, all the little pieces are demonstrated in laboratory settings already. And it's just a matter of putting the pieces together in order to realize this. So this is a sort of technology that we'll really see, I think, in the next decade or two. Okay, so what Emil and I discussed, we were chatting about this, is what would this allow you to see? And he said, well, imagine you had a network of entangled telescopes in space. Okay, space is nice because you can put these pretty far apart. We could say put them 10,000 kilometers apart in space. Okay, and we use this trick of sharing entangled photon pairs between the two telescopes to effectively allow them to interfere the light coming into one telescope and the light coming to the other telescope to make a huge synthetic aperture. Okay, so let's just run the numbers. What is a, okay, 10 to the 4 kilometers, the wavelength, let's say make it a micron, like visible light, red light. That corresponds to an angular resolution of 10 to the minus 13 radians or 20 nano arc seconds. These are numbers that are so small, I don't really have a sense of what it is. In order to get a sense, you actually have to think about on like astronomical scales. So let's do that. Let's take a look at Earth. Okay, here's Earth. Let's zoom in a little bit more. Okay, zooming in on the eastern seaboard, zooming in on New York, Turns out that Manhattan Island is about 21 kilometers across. Okay, 21 kilometers. Now, zoom out a bit. We've got this 21 kilometer long city, Manhattan, and let's go to the nearest potentially habitable exoplanet, Proxima b, some 4.2 light years away. 4.2 light years turns out to be 10 to the 16 meters. Okay, so if you have 21 kilometers divided by 4 times 10 to the 16 meters corresponds to an angular size. That is, that's the size, the angle that Manhattan would subtend if looked at from Proxima b is 100 nano arc seconds. Okay, on the previous slide, we figured that the resolution would be 20 nano arc seconds. So that means that if there happens to be an entangled network of orbiting detectors, telescopes around Proxima b, they would have the angular resolution to resolve Manhattan. And they'd be able to see Manhattan relative to Long Island, see the shape of the eastern seaboard, they could see all these things. Okay, or put another way, if we build one of these entangled networks of telescopes on Earth, orbiting Earth, we would have the resolution, the angular resolution, in order to see such features on this nearby planet. Unfathomably far away, unfathomably small, but enabled through quantum technology. So let me summarize the take-home lessons from this talk. If anything, I'd like you to appreciate that the power of exponential, that is, 2 to the n can be unfathomably large, even for modest n. For n equals 50, 64, 266, this number becomes absurdly large. And our technology today allows us to access this modest n, 50, 10, maybe up to 100. So we have the ability to create complex systems. And these are systems that are controllable in that you can prepare specific states and create specific amplitudes of superposition. But of course, when you measure, say, an entangled network, you still are subject to quantum randomness of the measurement outcomes. But the challenge that we're working on, and many researchers in the world, is to apply this incredible complexity and the power enabled by quantum technologies really to advance all areas of science and technologies. And this ranges from the microscopic or the nanoscopic, where we're using single color centers in diamonds to image the local environment inside materials and biological samples, all the way to the largest scale where we're thinking of these entangled networks of telescopes to look at most distant reaches of the universe. So that's the end of my talk. I hope I've painted for you the really interesting promise of quantum technology in the coming years. And I'd be happy to take any questions that you have.
Yeah, so thank you very much. I mean, so actually quite a few questions in the chat, and of course also you can just unmute yourself and ask questions as well.
Yeah, so Ken Coppersmith had asked, what does it mean to be controllable? And I tried to address that here. The controllable means is that they're able to choose the gates, the initial states, and to create, in some sense, in a deterministic way, what entangled states they make. The funny thing about a quantum computer, it has this incredible complexity, but then when we measure the outcomes, we do get just 53 bits of information out. So there's a lot of stuff going on, but not that much stuff comes out. And so you can't control exactly what happens, but that's somehow the ability or the power of it. One of the underlying powers of Shor's algorithm, which is a really complicated algorithm. It took a student of mine basically a year to try to teach it to me, and I forgot all about the beginning, by the time I got to the end. But it relies on quantum interference and this idea that certain answers can have constructive interference, they happen more often than others.
Can I ask a quick question?
Another question.
Oh,
Yeah, go ahead.
Uh,
Go ahead.
Are the outcomes reliable? In other words, given the same set of inputs at two different experiments, will you get the same outcomes?
They're not reliable, and that's, but their probability distributions are reliable. And so
Okay.
when I say that this string and this bit happens with a probability of 1 in 1,000, then we can observe that that's the case.
Okay.
And so you have to run the experiment many times to get the sort of probability distribution. But that's what's happening in their experiment, which is called boson sampling.
Can I ask a question?
Yeah, please.
I want a question about something I just read about this a few days ago called quantum volume. There's a new company called IonQ. It's a spinoff from University of North Carolina and Duke University, private company that is using a trapped ion method of quantum computing that they claim is much more reliable at lower temperatures, room temperatures. And they have something called quantum volume, which they say measures the computing power of a quantum computer much better than qubits. It incorporates qubits plus the amount of error messages you get and the amount of duplicated messages you get, and it puts it all into one figure called quantum volume. And the Google computer in the summer that did the calculation in 300 seconds that would take 10,000 years on a regular computer had a quantum volume of 4, and the previous quantum computer before that had a quantum volume of 2. This new trapped ion in just 4 months has a quantum volume of 2 million. And it's only a 3-qubit quantum computer. So can you talk about quantum volume as a issue here?
Yeah, so there's lots of ways to benchmark what the power of a quantum computer is. And it's true that Google's device was not working at all in the sort of most ideal way. When they read out these 0, 1, 1, 0, 0, 0, their chance of getting that right was less than 1%. So it's riddled with errors. Yet the underlying complexity is still there. And so in their case, in terms of quantum volume, may be a quantification of how useful a computer is for certain tasks, for example. It was useful for one task. But what's powerful about the result is they were still able to demonstrate that there was a task their computer could do, or their circuit could do, that would be really challenging to do other ways. I should, of course, point out that quantum technologies are advancing in many areas, and ion traps and these sort of superconducting qubit computers that Google used are sort of neck and neck. They have different strengths, different weaknesses. So it's a really exciting time because the different technologies challenge one another. They have different advantages and disadvantages. Many people feel that really the future is going to be using some heterogeneous mixture of these different things. Some things are better for some tasks. Some things are better for other tasks.
I have one other comment, and that is the president of this company mentioned that he believes that the number of qubits in quantum computers, I think he's trying to create a new Moore's law, he thinks is going to double about every 8 months for the foreseeable future.
Yeah. Yeah, so
that would be
pretty much
faster than Moore's law by a chunk, which is every 18 months.
Yeah, so pretty much any metric you put on these quantum technologies, you can see that things are improving with a Moore's law improvement. The challenge so far has been that the end point of that improvement in technology is still very far away. What's exciting about the examples I've given here, but really they're about measuring, sensing, and observations, is those are advantages we can get today, and we can use with relatively few qubits. There's a question here from Sunny Lin saying, how do we make the two photons and the two telescopes quantumly entangled? There's another question about how we need reliable methods for creating these entangled photon pairs. West asks, how far apart can the mirrors be and still accurate? Let me paint a picture that tries to give the sense of how that works. In order to there's lots of ways to create entangled photon pairs, but one of the most common ways to do that is to take a process where you take one photon and you split it into two photons. And now those two photons have a relationship that have to add up to the first photons. They have to be going in sort of correlated directions, so the momentum matches. They have to have energy that's correlated. And again, their polarization has to be correlated as well. And so if one has it's called spontaneous parametric downconversion, you can create these entangled photon pairs and they head off in different directions. And as long as the attenuation is not too bad, they can get quite far apart before anything messes them up. Now, they share a quantum state, even though they're far apart from one another. And so when I measure one quantum state of this photon here, it immediately determines the quantum state of the other photon on the other side. And so that's the non-local connection. Sure, it happens faster than light, the speed of light. This really boggles people's minds, but it's that idea that you have this connection between the two photons, but it's not determined which one. They don't have determined outcomes until you try to interfere them. That is the key to the entanglement between the two telescopes. Now, the challenge with the telescope was to get the photons to interfere with one another. Why is it easier now to send entangled pairs to the two telescopes? And that's because there's a way to build something called a quantum repeater. That it's this photon comes this far, and then we find a way to take an aspect of a state and then create another photon that takes it along without destroying the entanglement. And so you just need to break the distance into a number of quantum repeaters that aren't too far apart. And so as I move the two telescopes further apart, I need, for twice as far, I need twice as many quantum repeaters. And so the cost in grant dollars we have to spend to do this grows linearly with the size of the telescope. Whereas the challenge to actually get the photons without this technology is get exponentially harder as the telescopes get further apart. So that sort of sets the size scale of what's practical. I think this distance of 10,000 kilometers was sort of a standard size of orbiting satellite networks. Maybe that's the size of the space-based gravitational wave observatory they're thinking about building. But yeah, we do need better ways to make entangled photon sources. We need better ways to do all aspects of this technology because it's all just barely working. And we're just still at proof of principle stages, but that's just a few steps from being in a place where we can really harness these technologies. Any other questions for anyone?
I have a question. In which direction is going for the small miniature kind of applications?
The question was, which direction are we going, or what was it?
Yeah.
Sorry, what was the question?
Yeah. When am I going to have a PC with the quantum chips inside?
Never, because I think one of the misconceptions I had about quantum computers, and I think we portray for the community, is that it's so much more powerful than a classical computer, but it's very single purpose. And usually those purposes are they're not particularly useful. And so we'll never, quantum processors will never supplant our normal base computers because they just work in a fundamentally different way. But they have powers in specific areas that are really surprising, and that's where we'll see them. So one place where I think we'll start to see quantum aspects used more ubiquitously is in a sort of a sensing modality. So something, a fingernail polish that measures your blood oxygen saturation. You don't even notice it's there. Ways to characterize the way, let's say, the proteins in your own body are behaving to predict Alzheimer's, maybe something you might have. Quantum actually is used in most of our computers. They have a quantum random number generator, which is useful on some. So these technologies are stuck in there as various places. But you could imagine sensors for accelerations and motions of your computer that are enhanced by quantum technologies. In my mind, those are the places where those technologies will creep in.
I ask because at some point there was a comment of combining, regular technologies with quantum chips, but I don't know. I'm not aware of how it's
Yeah. Yeah, and every useful quantum algorithm or things relies on a huge amount of classical technologies and classical computation. Right now, the one sort of most promising near-term way we could use these quantum computers is something called the variational quantum eigensolver, which just uses the quantum computer for the one part that's sort of hard to do classically, but uses classical computers for everything else. There's also a question about, is there a role for artificial intelligence in working with these quantum systems? I think that that's a really interesting area. There've been a few studies, sort of, can you teach a artificial algorithm or neural network quantum mechanics without telling it the rules of it? Does it infer the complexity? Can it see deeper into it? And so there's an exciting area in terms of trying to bring these different pieces of technology together.
There was some time ago some scare about all the encryption algorithms going to be broken because of this technology.
Yeah, so it's still a very long ways away.
Okay.
And in fact, my professional opinion is that, certainly not in our lifetime, not in any lifetime will we be factoring numbers with Shor's algorithm. The power of it is it put a flashlight on a potential, and that was enough of a potential for some of the brightest minds to work on quantum technologies for 30 years. And now we're in a place where we're like, okay, well, still really far away, but we can do all these things in the meantime with the quantum technologies. And those things are much more interesting. They have to do with understanding chemistry better. They have to understanding with looking deeper in the universe, things that are much more fun. And of course, or not necessarily of course, but if we're worried about quantum factoring Shor's algorithm, breaking encryption, well, quantum mechanics also has a solution to that, in that these entangled photon pairs can be used for secure quantum communication. And that's technology that's actually already being used today. So it's both a problem, could be a problem, but it's really a solution that's even stronger.
Another question?
Thank you.
Yeah.
Another question from Mariana Riley's position. Is there anything on the forefront with examining cell membranes, let's say, in biological systems? Where can we go better than immunoelectron microscopy, let's say, which would get to a little bit of the structure of the cell, but doesn't really get into the proteins that are and the lipids that are part of membranes, or the microsomes where proteins are put together?
Yeah, so where can we go? So it's not an area that I work in specifically, but we have a few scientists at WashU and colleagues that are working very concertedly on building quantum sensors that are applicable in sort of those room temperature, liquid state measurements.
Yes.
And one of the promising technologies is one can create a quantum system in diamond. It's a little defect in diamond. It's called the nitrogen vacancy color center. And this nitrogen vacancy color center is so small, and because of its quantum properties, it's to be very sensitive. And so it can measure things about its nearby environment with incredible precision. And so there's some scientists working on ways to harness that to sort of study, what are the processes happening on certain biologically relevant timescales in, say, real time. I've worked on ideas to measure temperature over nanometer scales and try to do that inside of plant leaves while it's undergoing photosynthesis. So there's a lot of really exciting possibilities in the nanoscopic scale using quantum systems because they're intrinsically small. And they're just starting to come into use. The challenge is to really come up with something that's better than an established classical technology. And that's usually hard to do, but something that we're working on identifying
Is there
are those
somebody
places where
here
it's
who
much
could?
better to use quantum technologies. Go ahead. Is there
Is there
somebody here?
somebody here who could who's working on something like that to talk to?
Yeah. So Matthew Liu, who's in the engineering department, works on nanoscale imaging. And we work together as part of the Center for Quantum Sensors, putting together a grant where our big effort is to measure electric fields at sort of a scale and with an accuracy that you can't do by any other means, and to try to uncover various phenomena in chemistry and in biology with that.
Thank you.
So it'd be nice to have a talk on that subject. That's something we can certainly add to the seminar series in the future. So there's I'll read a couple more questions from the chat here. The light gathered by a telescope starts at the celestial object far away. How do we get the entangled photons to play a part of that? And the way to think about, one way to think about this is there's a technique called quantum teleportation. So you could imagine your light from the celestial object comes to one telescope, and now we use entangled quantum state to basically teleport the quantum state of that photon to the other telescope, and then we see if the two interfere. And so the entangled photon allows you to take the light from one aperture and get it to the other aperture without any penalty. And that allows you then to overcome the exponential challenge of getting that photon across the thing without measuring it and therefore breaking the interference. There's another question. Can you tell us how gravitation factors in on developments in quantum technology? This is an interesting point, because one of the biggest unsolved problems in science, quantum physics, I suppose, is how do gravity and quantum mechanics fit together? And so one of the things that many people are interested in is, if we have these really sensitive quantum sensors, can we start to see perturbations to the rules of quantum mechanics due to gravity? Can we see that gravity changes entanglement in certain ways, or does it collapse entanglements? Those are really exciting questions that people are working considerably on. We don't know how gravity factors into quantum technology and how it fits with quantum mechanics yet, and that's an open question in physics, which hopefully will, as we continue to refine our use of physics and quantum technology, we'll start to understand that. Then there's another interesting question. To make a bigger observing platform than Earth, can we use the fact that Earth is rotating, as orbiting? And that's an interesting question. I want to say for sure that the answer is no, but the idea of when we talk about this synthetic aperture idea is that really the photon emitted from, say, some object we're interested in, there's two possible paths light takes, and that's why it interferes. It's basically the same photon follows both paths. And so if there's a big time delay, it's not going to work, because now those photons are not correlated, or they're not the same photons with the previous one. So there's not a way to use the fact that we're now and then later at a different time to get around this Rally criterion. But there are, I'm sure, other things we can use with Earth's motion to determine something useful, but I'm not an expert in that area. Yeah, so we could set up a telescope on the moon and entangle with Earth. Absolutely. This is a sort of, there are, more and more technologies where we're able to send entangled pairs to satellites. And so all these pieces are coming together. There's, of course, other challenges to doing this that I haven't thought about. For example, do we get enough photons from Proxima b in order to see something meaningful? Those are all things we have to look at, but maybe the biggest challenge of angular resolution could be solved with quantum technologies.
When you were talking before, I thought you were referring to LISA, that is better than waiting for, for a year. It's just having a telescope at the distance of the Earth to the sun at 60 degrees advanced or retarded from the position of the Earth. That's a much bigger, length of telescope than the idea of circling for a year.
Yeah.
I don't know if they're going to use
Definitely.
this for LISA. LISA is to come earlier probably than when they had this technology available for.
Well, if there are no further questions, it's been a really wonderful chance to present these ideas to you. It's something we're, of course, very excited about here at WashU and within the community, and I hope to share more exciting updates with you in the coming years about how quantum technologies continue to advance.
Yeah, thank you very much, Kater, for a great talk. I guess if there are no other questions, we will stop here. So let's thank Kater for a wonderful presentation.
Thank you.
All right. Bye-bye, everybody.
Thank you.
Bye.
Excellent.
Thank you.